In the last video, we developed the test of exact differential equations, and we numerically tested it as well. And we found that this given differential equation, that is this equation, was an exact differential equation. So in this video, we will learn about solving this differential equation, and there is a set of 4 steps that is followed in solving an exact differential equation. So let's try to understand these steps one by one. The first step basically is about developing a preliminary function, because we know that the function that we are talking about is which is actually the solution for which we are looking for, will be in terms of y and t, because y is likely to be a function of time, just like we usually do. But since the exact differential equations appear in this function form, we have written f y comma t, and we have kept the constant on the right hand side, which is not mentioned here because we only need the left hand side. So if I have this as the preliminary or the tentative or the semi-final, not the final version of the given function, which will be the solution at the end. If I take the derivative of this function and also take the integral with respect to y, for example, the answer will be the same, because derivative and integrals, they cancel out each other. So this is what I have done. This will remain the same if I, with respect to y, differentiate it and integrate it with respect to y again. So they will be cancelled out, this delta with this elongated s of integral, they will be cancelled out, and it will remain the same as it is. However, there are 2 terms that should be added, because you know whenever you integrate, you will get the constant of integration, and whenever you differentiate, you need to remember that the function can be in such a way where there are terms in which t is appearing separately, for example t plus t square. So if such terms are there, and if we are differentiating with respect to y, these terms, the answer of these terms will reduce to 0. So when we differentiated here, we should know that there is a possibility of having t as some additive term. This is known as additive term, because it is being added. You can see these pluses are there, and t is appearing separately. It is not with y. If it were with y, it would not have been deleted, or it would not have become 0. But for those terms that are only of t and are being added, they would have disappeared with the derivative. This is why we give a small place for them, that there would have been some additive terms of t for which we are leaving some place. So we write them with f of t, that is all those terms that are containing t. So you see that we have done integration and differentiation, and it leaves no effect except for bringing in the constant of integration and terms that are in terms of t. This will help us, so we go ahead and we combine c and f of t into one term, that is psi of t. Because c is a constant, even if I merge it into in a function which is in terms of t, it will remain in terms of t. So you can see both of them are in terms of t. However, we have used a different symbol for it, that is psi, that is the Greek letter in this case. So instead of writing separately the constant of integration, we have combined it with the terms containing t function, and now the expression is getting simplified. And now we know that psi t has 2 functions. One is the constant of integration and other terms containing t. And these are the 2 components that I have written separately. You can pause the video and see that we are talking about the same thing. However, it is written in other words here. Now we remember that delta f over delta y was equal to m. We assumed it equal to this. So this is all assumption that we have done in the last video. You can verify from there. So instead of writing that whole delta f over delta y, I am writing m here. And we must remember that it is being written instead of this term. So this encircled term is now smaller, that is m only instead of the whole function, right? So now we have a simpler function. Now we have the value of m from the given equation. We need to recall that in the last lecture or the same part of the same video, the value of m was extracted, it was 2yt, and the value of n was y square. So I'm going to use the same values by comparing with the standard form of exact differential equation. Now this m is here, we have substituted the value of m, and then we can solve it using the simple process of integration. So in integration we have another c which is produced, and we can add it in the psi t function without getting it affected, because you know constant when gets added into a function, the function will still remain in terms of t, and even if we don't change the symbol it doesn't affect, because if the functional form of psi t changes, that is if it was t square before and if it becomes t cubed in another example, then we can use some other symbol instead of using the psi symbol. So it's now it's nothing new here. If I add c in it, it's just going to change slightly, which is not going to affect the functional notation of it. Now this is the first step of the process, that we have simplified it, and now we have the preliminary result in this form, in which this is a known thing but this is an unknown thing. So for that, this unknown thing, we definitely need to do some calculations to find it out. So these are predefined steps. The second step is here. The clue of the second step is simple, and it is that we have used the value of m in the first step, but in the second step we can use the value of n, because that is also a known thing. Now it is given in the given differential equation, so I can use this value. However, I should know that it is equal to this. So I need to have this term here somewhere, so that I put the value of n and then it can be a a simplifying process. I should remember that what is the value of n here. I have to go back to see in the given differential equation, it was y square. So y square is the value of n that I can definitely use once if I bring n in the process. Till now it is not there. I have used m but not n. So for that I guessed that since n is equal to delta f over delta t, I can take the derivative of the given function with respect to t, and it will become n. When I take the derivative, right hand side will also be factored. The major change is this, that psi t becomes psi bar t, whereas this derivative is very easy. However, on the left hand side, this function is now this, and simply speaking, by getting rid of other unnecessary terms, it becomes delta f over delta t, which means that now it has become n. Therefore, in the next step, we highlight that delta psi bar t is still unknown. However, we know the value of this, which is n, and n has a certain value that we can use in the steps ahead. So what we did is, instead of writing this, we are going to write n here. So you saw that instead of writing this, we can write n, and we know that the value of n is y square. We just looked in the given data. So we substituted n and we wrote y square, its value, in its place. And incidentally, we have y square on the right hand side, which gets cancelled out, and finally we get psi bar t is equal to 0. So if the psi bar t is equal to 0, we can get to the value of psi t as well. And for that, there is that next predefined step, which we have to remember the process of it. It tells us the same thing, that we have found psi bar t. We can find psi t simply by reversing the thing, that is reversing this derivative, that is by taking the integral. Integral will cancel this derivative out, and when we take the integral of this derivative, they will be cancelled on the left hand side, but it also tells us that what will be on the right hand side, because the derivative is 0. So, actually it would be some sort of constant, the derivative of which is now 0. So, this is the constant that we will get, because whenever you integrate, if it is 0, it becomes a constant. So, 0 can be the derivative of a constant. So, we write constant when we take the integral on both sides. Integral is written, this term is written as it is, and we write k here because k is the substitute of a constant whenever we are to integrate. So, a constant is primitive of a derivative. Whenever there is a derivative equal to 0, the primitive or the original function was a constant. So, we write it in an expanded way. It becomes a derivative of psi t. It gets cancelled out, and we are left with the original function, and it is equal to k. So, now you can make sense of it. If I take its derivative, its answer will be 0. So, it is satisfying this given equation. So, you can understand it in a more detailed way by looking at this explanation. Simply it was taking the integral. So, now we come to the fourth step, which is the easy thing to do, because in the fourth step we have the values that we needed. In the step 1, you remember we developed the preliminary result. Now, I have the value of psi t that I can put in that step 1, and in the step 3 I just got this value. This was step 3 in which I got the value of psi t, and I am going to put it. So, this is step 1 in which I had psi t as an unknown, and now I have found the value of psi t in the step 3 that I will put here. So, instead of psi t I am writing k, and now I have this in a better form. Now, since it is an exact differential equation, we just verified by using the exactness test that you saw in the first part of this video. So, we can safely assume that the differential of this function, which is here, will be equal to 0, because it is an exact differential equation. This was the condition of it, and if it is equal to 0, then originally it would be a function which was having a constant on the right hand side, the differential of which is equal to 0. So, it means that instead of writing f y t, I can write c f, which is the constant which is generated here due to the differential that we have calculated. So, instead of this I can write a constant, and this means that I can carry this to the next step. I have shifted the other constant from right hand side to the left hand side. It was k, and now it has become a negative value. Mirroring the image, I will get this y square t will be equal to this. Now, instead of writing two constants as a difference, I can write them as one constant, which is now c bar, and this can be the solution of the given exact differential equation. And it is synonymous to the standard form. This is the standard form of the function that we started with, the differential of which is equal to 0. As you remember, the same condition that we have just used. So, this can be the final result. However, this is the equation form. However, we need the solution form, and in solution one variable is in terms of other, not together on one side of the equation. So t has to be sent to the other side, for which we are going to make these adjustments. We are shifting this t to the other side of the equation, and we will get this thing. Y square is there, we need the value of y, not the y square, so we take the square root. Square root appears here, and t is introduced here because it is the independent variable, and time path of y is now being simplified. Constant, the square root of a constant will be yet another constant, which is represented with c, and t can be written like this, and then being reciprocalized, t 1 over 2 becomes t raised to the power minus 1 over 2. So now it is a suitable time path that we wanted, and it is the time path or the solution, general solution, because still there is an unknown constant in it, or arbitrary constant. So it is still a general solution, not a definite solution of the given differential equation, which was this, and this is the solution of this given differential equation. So in this way we can find out the solution of a given differential equation, and it had a few things that we had to calculate. Primarily we defined that what is a differential equation by taking its total differential, and then we developed the exactness test condition, which was in the first part of this video. But in this specific part of the video, that is the second part, we have solved the exact differential equation by using the 4-step procedure, which is used in solving an exact differential equation. And there were these steps that we performed on this given numerical exact differential equation. And from first step we found a preliminary result. In the second step we introduced the value of n. In the third step we found the value of psi t, and in the fourth step we substituted the value of psi t to get the function and the solution, and then it was transformed into a specific time path form, which is the most ideal form that we are looking for, that is y in terms of t. So here we have time path or the general solution of an exact differential equation. Now we are capable of solving other exact differential equations, primarily by checking their exactness by exactness test, and then by using the 4-step procedure. Thank you.